We are in week 9, and this is chapter 7, and we're talking about power distribution. What is important about this chapter is you have to recognize what kind of power are you receiving in a building, and how does the power distribution work. We talked about Ohm's law, we talked about the power in your house, how do you connect your boiler, and now you need to learn the whole power system coming up. And we learned about the power plant, right? I think this week you're going to visit a power plant. So it's good to have an idea of how does the power system work from the station all the way to your house, and how do you recognize power distribution. So current is the flow of electrons. This thing is turned on. We have DC and AC. DC is constant. DC, as Tim said, comes from a battery. It's chemical. It comes in only one direction. AC is alternating, so it comes from cyclical matter, like a rotor spinning. The rotor is spinning, so it goes back and forth. And as you've noticed, we'll talk about something called the power factor. So the power happens when the impeller here or the rotor spins. The highest power will be when you meet your coil. As you go further, the power will go low, then it goes down, and it circles again. So there's always power. It goes to zero for a slight second, then it goes back again. So it's very cyclical. So alternating comes always from cyclical motion. Something has to be going in circles. That's what comes in a wave, sinusoidal wave, and that's why it's alternating.
It's counterclockwise. It's counterclockwise.
It doesn't matter. Could be either. AC, most equipment are using AC, and they're more reliable because motors usually are brushless. There's no touching parts. If you take apart an old motor or a hand drill, you'll see there are two little brushes touching the rotor to reverse the current. And over time, they will wear out. Just like they look like the brakes in your car, the brake pads. Eventually, they will wear out, and you have to change them, and there is no connection. AC equipment is cheaper and more trouble-free than DC because you don't have to change the brushes. AC is easier to produce, it keeps things circling. We talked about the power in Niagara Falls and hydropower. Wind turbines are all AC, makes sense because we are spinning turbines. So whenever something's spinning and generating electricity, it is alternating current. We agree on that? Whenever something is chemical or a battery, it's producing DC. Like photovoltaic is DC. Your car, DC. Battery, DC. Chemical reactions, one voltage at the same time. Electrons flow that alternates, represented by a sine wave. This is the sine wave. Cycle and frequency. A cycle is when you start. What's a cycle? You start from 0, you come back again, 360. That's a complete cycle. Frequency is how many cycles do we have per second. So far, for our power production, we have 60 hertz, 60 cycles per second. Can we do more? Yes. Can we do less? Yes. But we agree that that's what we're going to use because we don't want to send frequency and we don't want to receive frequency, so we have to agree on the same frequency. Same with the radio. They send the frequency and they tell you, okay, if you tune into this frequency, you will hear us. Otherwise, you will not. Otherwise, it's a different frequency. So the frequency of the radio is the same thing, just a higher frequency. Give me a frequency of one channel, 109. That's 109 gigahertz. And we had AM radio. We had FM radio. What is AM? You guys remember AM? Since you guys are learning basic electricity, I just want to touch base on these little concepts. So this is my frequency here. And we said from here to here, that is hertz. How many? This is 1 hertz, 1 frequency per second, which is very small. What do we call this part?
Peak
Peak voltage, thank you. And it's also called the amplitude. how high do you go? So if I want to change this wave, what can I change? I can change either the frequency or I can change the amplitude. And we have a voice frequency. You can have this voice frequency connected to this frequency, and the wave frequency will go riding on this frequency. I'm very simplifying the idea, but this is how it goes. So we have frequency, and whenever we go to this frequency, will be received by the other station. So for AM radio, for example, we can change the amplitude. So if there's a wave that goes a little bit higher, we're not going to catch it. This is what we are programming the radio to receive. So AM is amplitude modulation. Modulation is just changing. So modulation. And they realize it's okay, but it's not as clear. It does not go as far as FM, which is what frequency modulation. You don't need to know this. I'm not gonna test you on it. Amplitude. So if you have an industrial radio, they have a frequency for TV, there are frequency for radio, there's frequency for the police, frequency for aviation, frequency for cell phones. So are we gonna run out of frequencies?
Yes.
We did run out of frequencies.
Wow.
Yeah, that's why they stopped some TV channel frequencies. We need this frequency for something else. So the cell phone can't cover everything because it's range. We can't go very high. There's a range of what we can use and what we can broadcast. So there's frequency for the TV, frequency for the GPS, frequency for radios. If you buy a small house radio, it has limited frequency. You can't listen to the frequency for like the police, for example, unless you buy hobbyist frequencies. Scanner, certain scanner, and they will sell it to you and they will give you that frequency. You can make your own radio and you can listen to all the frequencies you want. But otherwise it's really difficult to high frequency. Some frequencies are dangerous to have, so they don't broadcast that everywhere. Like for radar, it goes from one tower to another, and then make sure that there's nothing in between. What about what about the microwave? Microwave is very, very high frequency between two sides. Look at the microwave side, there's a megatron, that's a better frequency, and there's something that receives it. And whatever goes in between gets really hot and activated. So that's why you can't run the microwave with the door open. You have to read the microwave. We talked about the positive and negative parts of the frequency, the sine wave. Everything is in a sine wave. We watched the YouTube, and this thing is tilted for some reason. I hope you can see it. So, when you go to a power plant, which you will this week, this is the power plant. What looks like a big rotor here, that's a turbine. So a turbine is a big wheel, heavy wheel, that has a lot of momentum, and it's connected to a generator. The generator is something similar to a car engine, big diesel fuel oil car engine. Sometimes it runs on steam using coal, and it turns out generator. The generator will make some electricity. So you're gonna have some transformers. The amount of voltage that comes out of this generator is huge. It's in thousands. It goes to a step down. Then we go to an aerial line. These lines are very thick. I showed you how thick they are. And you go to a substation. The substation is stepped down to smaller poles and smaller wires. And it goes to 50,000 volts, step down transformer. So we keep going with transformers. And transformer that we saw, they work with induction. Similar thing with transformer we saw, the little one, but this one is a bigger scale, a different technology. Until we go back to the consumers. So we have commercial consumers, industrial consumers, and a house. I will stay at a house, you'll see those little things in the street all the time. There are breaker and switches, and they also have an overload protection. And your house will be supplied by 220 volts. Within a limit, there's a 220 volt, and I think it can go up to like 3 kilowatt hour. It's how you agree with the power company. The power company will come and look at your house and will give you amount of voltage to use in the house. You can ask for more, you can ask for less, you have to have different permits. So houses have like different, how can I say, category, the commercial and consumers. If you use a lot of machinery, probably it's not going to be enough. And in some states, even here, they will start charging you different rates. So if you consume for example, 1 kilowatt hour, it's going to be 15 cents. If you're consuming 2 kilowatt hours, it's going to be 30 cents. If you consume more than 3 kilowatt hours, it will be 50 cents. The time makes a difference, and the amount makes a difference. So the price changes based on the time and based on your consumption. So
that's why when you get an apartment that you have to pay, electricity is included, they have a certain rate.
yeah, and they have a limit. They give you a flat rate, assuming you're going to use this much. And if you exceed it, probably your landlord will contact you, say, hey, what do you have? They probably estimate, you have a microwave, you have an oven, you have this and that. They give an estimate of how much you're gonna consume, and if something goes wrong, they have to check because they will know that something is wrong with the consumption. And soon enough, we'll have smart metering systems. The smart metering system basically communicate with the live, with the power station. They'll say, hey, this person is consuming 2 kilowatts per hour today, what's going on? Could be something wrong, it could be he's plugging in the wrong equipment, and he could be mischarged. Maybe your neighbor is tapping into your power, and this happens a lot, especially with big buildings. So that's the power coming to your house. If you go to commercial and industrial, this is where you have, they require more power. They have bigger ACs, bigger equipment, they might have mills, they might have lathe machines, they might have some cleaning appliances. So we'll go with different power, usually 480 or 408, and they give you also 3-phase. The option of having 3-phase power. I will talk about what does 3-phase mean. Okay, we talk about effective voltage, and we said the peak voltage here, as Dave said, is at the top at 90 degrees. This is 8 degree. This is 90 degree. This is peak voltage, and the effective voltage is 0.707 of the highest peak voltage, which is around here. That's how you average it, and that's where you have your 45-degree angle. Peak voltage at 90 degrees, same thing, and this is the effective voltage here at 45-degree angle. And this is also something called the power factor. It depends also on the wave, the strength of the wave. This is the power factor. The power factor is the ratio between the effective voltage and the peak voltage. So what is my power? I'll talk about it a bit more too. Phase. Let's talk about phase a little bit because that's very confusing. Not very confusing, but it's important to know. And you might face some equipment with more than one phase. And in a very basic way, we can say that if we look at this rotor here, we had one coil. So at some point, the coil will be at 0, away from the magnet or from the other pole here. Somebody thought, why don't we put more coils in equilibrium? If you have one coil, or just 2 coils back and forth, there's a possibility at some point for the motor not to move because it will be far enough with enough momentum and it's going to be stuck. If we have 3-phase, And this is the best configuration between with 120 degree between them. This kind of power is I'm talking about generation now. So this will be plus and minus, plus and minus, plus and minus. So every time this rotor moves, it will move 3 currents in the same time. There's a current going on here. 3 currents at the same time as it moves. So what does it look like on the wave? One will start at around 120 degrees later, which is around here. Another one will start. Another 120 degrees here. Third one will start. So why do we need that? More power. 3 currents riding in the same wave. To give you more power, it is very needed for big motors. A lot of big huge motor compressors are run by 3-phase. There's no way that this rotor will stop because it's always off balance, rotating and pushing. It's not going to be in equilibrium because it is off-centered. With single phase, we have one current. There's a possibility that the motor would not start. For example, did you ever have a motor that you plug it in and it starts humming, but it does not turn? So you always need something to push it. Usually that's a capacitor. Capacitor charge, and then you push it off center. The best example of that is you go to a compressor outside. You turn it on, and it's humming. You try to push the fan with a stick, and it starts running fine. You just knocked it off balance. At some point, get to a point with plus and minus at the same time, the same amount, the same ways, and it just going back and forth. You need to go off balance to start the cycle. And that's why we usually need capacitors to push the motor out. So, talked about alternator already. A phase is the number of current alternating different time.
So
different
each
intervals.
sign is a phase.
Yeah. Each sign is a phase, each current is a phase. Number of current alternating different times, intervals in a circuit. Single phase, 1 current. 3 phase is 3 currents. Why don't we have 2 phase? Do we have 2 phase? I don't think there's 2 phase. Not that I've seen so far. But 2 phase will have the issue of
Motor gets stuck.
yeah. Oh, it's gonna be this way. And if you're going to have them equal, you will have them this way. And you can run it, but there will be a point where it will get stuck. So either single phase or 3 phase. Alternator and current, the number of winding depends on the desired number of phases. So let's talk about that a little bit. This is the winding. If you look at this winding, you'll see there's a metallic part between each two that completely opposite to each other. There's one in front of the other one, and each one of those is different winding, in different strands, and these are forming a magnet, and they are aligned in a way that they will not be all facing each other completely. There's a little bit of offset, so it will not require a capacitor. There's always going to be off center once you follow it. So these are the windings. So the strength of the motor is dependent on the number of windings, the strength of the windings, and how strong the magnet are you generating inside. And the number of phases has to do with the outside windings. This is a motor, it's not a generator. The one that you have that absorbing the current from the rotation. Does that make sense at all? Phases, current, winding, magnets. We are transforming magnetism into current, and we said there is a change. There is a relationship between movement and current. If you move copper near steel, you will have some kind of energy. We are using this energy to make electricity. This is the single phase and 3 phase in rotation. You don't need to know all the electricity, you're not going to the electrician. I mean, you can, but you have to go through a different kind of course study and have to understand how to calculate power factor. I need some training. And probably will be also some kind of math involved to be able to understand how the power works. But for us, as HVAC technicians, or even if you go into power generation, those basics will go with you further. Sine waves, so there's 3 phases being offset by 120 degrees. Why do we need to know about 3 phases? Because the layout is different than 1 phase and 120. So 120, how many hot legs do we have?
120?
Yeah. Huh?
Hot
Yeah,
legs?
yeah.
Oh, one.
1 hot leg, 1 neutral, and a ground.
I thought you said how many legs? That's it.
That's 120. 220, 2 hot legs, and a ground. No neutral. So remember that. What about 3 phase 220? What are you gonna have? 3 hot legs. 3 hot legs. So each one of them will be hot. And if you go into a circuit breaker, the hot legs usually have what on it? A fuse. If you see a fuse or a breaker on the line, that's a hot leg. You do not want to put safety switches on fuses or, on neutral. You're not going to put circuit breaker or a fuse on a neutral.
3 phases, they're usually from big, from record.
Yeah, we have few ACs here that work with 3 phase. Why do we want to use 3 phase for compressors? More power? Does it need capacitor? No? No capacitor is needed. Capacitor here for start, it runs smoother, has more torque. However, they consume a lot of power. That's why you don't have 3 phase in your house. And the wiring is more intricate. And they will send you 3 currents. So are you going to pay for it? No. But 3 phase is more powerful. If you go to lathe machines, milling machines, they're all 3 phase. You need a lot of power. Some motors are very strong. There are motors like as big as this TV here. I've seen motors like as big as those 2 tables together. If you go to any milling machine, whether they make rubber or they make food, you need a lot of torque. And there are motors that can provide that torque based on the winding inside. So the winding is everything, the way how it goes back and forth, and you always want this one to be intact, which doesn't like go bad at all. And if you notice these motors are very, very reliable. Does not have a capacitor. Why do you think they put the winding in the stator and not the rotor? It's not necessary. You'll see it either way. But what do you think one reason that you put the winding on the stator? Just you have to guess. So it doesn't move. It's moving at like 3,600 RPM. It's easier to leave the stator with the winding intact here instead of moving it the entire time. And there are different configurations. There are very small motors with hair thin wires going through it. You're always going to have copper wire somehow or magnets. What about those RC motors that run with the battery with like little toys? Do they have windings? No. They don't have windings. They have permanent magnets. Small little permanent magnet. That's enough to give them the power. I have yet disassembled one of those drones motors, which is this big. I haven't had a chance to see what's inside, but probably something similar, different induction material. Inductors induce voltage that counteract the original voltage. So, as we move the motor, there is voltage being produced based on movement. It counteracts the original voltage, and that will cause the motor to run. Reactance, resistance that alternating current encounters when it changes flow. So inductance and resistance are 2 things that happen in a motor. Inductive and capacitive reactance, you don't have to remember that. Impedance, the sum of both resistance and reactance. We do not need to know this. We just want to be aware they exist. So as the motor moves, the rotor is moving. It will have some inductance, which is voltage happening from the movement, opposite to the provided voltage. You also have some reactance. As we move the voltage coming in, we'll have some resistance to the voltage being produced. So there's something called the impedance, which is something work against the rotation that is caused by the voltage being opposite and the same. I'm not gonna ask you about that, but at least you know the terminology does exist. I don't think you will need to know that unless you become an electrician that works with like motors. Power is calculated by the voltmeter, and the meter gives the apparent wattage. So if we are producing, how do you calculate power? How do you calculate power? What is the power law? Voltage times amperage. So we will go and calculate how much power I'm getting out of this alternator. That's the apparent voltage. What do we see? The power factor and is the ratio between the true power and apparent power. So the true power is what I'm getting in the wire. That's what I would put my ammeter on and measure the amperage. And the apparent power is what is calculated, what is theoretically given by the motor. That's something called the power factor. Yeah. So power factor is the true power over the apparent power. So I am seeing 119 when I measure with the tools, and this is rated at 169. So the power factor is around 0.707, which is related to the what we talked about before. That is the power effective voltage. Again, we're talking about power generation and power factor. It's what this alternator is designed to do, which is peak voltage over here, and what is the actual voltage and my power factor. So if you hear power factor, that's what they mean. It's your power effective voltage at 45 degree angle. So now at least you understand what is power factor. You'll hear that a lot. And the power factor does change from one place to another based on the wave. It's not always at 0.707. Cut the list could be more.
So is that's
Yeah.
the effective voltage.
Yeah. You know what is this pump for? That just turned on?
Cool down his room?
Yeah.
I'm saying.
There's 80 in here for hot.
It's hot?
Yeah, so we opened that door, man. I took off my sweater. I was like, whew. Our ears are red.
It's 80.
That's
the same.
How do you have a scar? You have a scar from it.
Hot. I'm sorry, man.
But you didn't finish why that's on.
Huh?
Oh,
You
yeah.
didn't finish
It's
it.
off.
No, why is the pump on?
Oh, the pump is
Is that
not
a return for water?
Yes. It's condensate pump, which means it's giving off heat here for no apparent reason. We don't want heat. So it's giving off heat. The steam is condensating, collecting, and being pumped all the way to building 17.
You don't have too much CFM.
Yeah. This is hot, man. Now that I know I'm really hot. Okay, I'll stop here and fix the heat.